Hello class, here we are at case study 2B part 3. It's time to answer case question 2B. Okay, so with case question 2B, we are going to read the case question again. We're going to start with the first 5 ingredients, set up our hypotheses, and then we're going to pick up with doing these steps that we were practicing with 1 through 7 in the previous video. Okay. So let's zoom this in. All right, so just a reminder of what our case question was. A statistics instructor used an online data bank to record the GPAs of the 90 students that had enrolled in his introductory statistics class over the last 2 years. The GPAs were collected at the time the student began the course, and the average of the 90 GPAs was 2.733 with a standard deviation of 0.762. The most recent report in university literature states that the average GPA of all students having completed at least 1 semester in residence at the university is 2.889. Is the GPA of students enrolling in introductory statistics statistically significantly different than the university as a whole? Okay, we're going to start with the first 5 ingredients, okay? So my population, I wrote as all students enrolling in introductory stats courses at this particular university, okay? And where that came from is our sample. So the sample are the 90 students that had enrolled in his introductory stats class, who we have GPA information on, okay? So we have the GPA information. The other thing to kind of note is that we are talking about this particular university. Okay, so population, all students enrolling in introductory stats courses at this university. Sample, 90 students at this particular university who we have GPA information on. Variable of interest, that which is measured from the objects in our sample, okay? So what did we measure on these 90 students? The GPA. So I have GPA of an introductory statistics student. If you just wrote GPA, that would be sufficient. Okay, the next thing we have is our parameter. So first, what's the symbol for our parameter? Since we're talking about averages, yes, our symbol is mu. Okay, the average GPA of students at the university that enroll in introductory statistics course. Now we have our statistic. What's the symbol for our statistic? Yes, that's going to be X bar. X bar is the average GPA of the 90 students from our sample. Kind of went for simplicity here and just wrote the words our sample. And what's the value of X bar going to be? 2.733. This is given within the problem. All right, the next question we have is state the null and alternative hypotheses. Okay, so I'm gonna go up here and kind of point out. All right, the alternative hypothesis always comes from the question we are asking. Is the GPA of students enrolling in introductory stats courses statistically significantly different from the university as a whole? Well, then this kind of bears the question, well, what is the GPA of the university as a whole? Okay, so when we go back and we read the problem, the most recent report in university literature states that the average GPA of all university students is 2.889. Okay, so we're wanting to test are these students, are all students that enroll in stats courses have a GPA that's different from the university as a whole. So mu does not equal, for HA, mu does not equal 2.889 versus HO, mu does equal 2.889. All right, so all of these steps 1 through 6 should be a review. We've been going over those since about the 2nd or 3rd week of school. All right, so something I like to introduce and make sure that we talk about whenever we are looking at the case questions are our type 1 and type 2 errors. Okay, so I will start with what's the definition of a type 1 error. Reject a true call. So first I start with what does it mean to reject HO and accept HA? It means that when you did claim that the average GPA of students at the university that enroll in introductory stats course is
different from the university as a whole. So try to use some colors to convey what I'm talking about. So what does it mean to reject? It means we claim the average GPA of a student at the university that enrolled in the introductory statistics course is
different from the university as a whole. Okay, so what I have in parentheses in purple represents rejecting. Okay, but this is an error, so we made a mistake. Okay, when actually the null is true. So that means that mu is not different from. It's actually going to be equal to. All right. Then let's look at type 2 error. A type 2 error is failing to reject a false null. So first we need to talk about, well, what does it mean to fail to reject? It means that we claim, I cannot write today. We claim the average GPA of the students at the university that enroll in introductory statistics course is not different from the university as a whole. Okay, failing to reject HO means we do not prove HA. Okay, but we made a mistake. Okay, we made an error. Actually, the null is false. So when actually that GPA is different from the university as a whole. Okay, so something we can kind of look at whenever we write our errors is, okay, which one of these errors is worse than the other? Okay, so we claim, so type 1 error, we claim there's a difference when there's not a difference, versus we claim that there is not a difference when there actually is a difference. Okay, so this problem, we don't really have any context besides an introductory stats teacher is just curious about this. He is wondering. So there isn't any set up to where like, well, if we make a mistake, this will happen, okay? He's not going on to report this to any higher ups. He just has a professional curiosity. Okay, so whenever we don't fear a type 1 or a type 2 error, that's when we pick alpha in the middle. Okay, and that's what we're going to want to pick for this problem. Alpha equals 0.05. And again, we pick alpha equals 0.05 because we're not afraid of a type 1 error or a type 2 error. Neither of these errors that I have written here have any bad consequences associated to them. Okay, bad consequences meaning, is somebody or some company, are they going to lose money? Are people going to, be hurt by this information? And both of those answers are no for either of these consequences. Okay, so we want to give the test statistic box the value of the test statistic. So test statistic, this is where we're going to pick up with how we were solving the last few problems from the previous note set. Okay, so do we have a large sample? Well, here, I guess maybe this would be a good time to kind of scroll to the top, and maybe you just want to make a note of any of those numbers that you think will be important. Okay, so now let's scroll down. We do have a large sample. Okay, so that means large sample, let's use the central limit theorem. That means we're going to use our Z test statistic. Go ahead, take a moment, plug into those, and see what you get for your test statistic. You should get around negative 1.94. All right, and then you're just gonna box in that test statistic value for me. The next step is the null distribution, the distribution of our test statistic. Well, our test statistic is Z. Woo. Our test statistic is Z, and Z always follows a standard normal distribution. Z follows a standard normal distribution. All right, next step we have is p-value. So, all right, so the way we always write our p-value statement starts the same. It's the probability of observing the value of our test statistic, or more extreme if HO is true. Okay, so we need that Z test statistic of negative 1.94. It's also going to be helpful to make sure we know what our alternative hypothesis is. HA is mu does not equal 2.889. Okay, does not equal 2. That's a two-tailed test, so we're going to have to start with multiplying by 2. So our p-value, 2 times the probability that Z is less than or equal to negative 1.94. So we're down here at negative 1.94. There we go. And we want, so our test statistic's negative 1.94. We want to go to the nearest tail and then double it. All right, so now we need to go to our Z chart and actually get that value. So we're looking at negative 1.94. So negative 1.9, we're on this row, and we want 0.04. So our number for one tail, the probability is 0.0262. So this is 0.0262, and this is also 0.0262. Okay. So again, just trying to help convey some understanding with colors. All right, the one-tailed probability is 0.0626. Okay, but then we have to double it to get our final answer. So box p-value, okay, the p-value is what I have boxed in blue, okay, 0.0524. Okay, so we picked an alpha of 0.05. So that's going to be helpful to know. Maybe I'll write that right here. Alpha equals 0.05. And so something we have talked about since coming back from spring break are the idea of errors, okay? And that idea of errors is just that since we don't know the whole population, we can't be, I don't want to say we can't be 100% certain. There's always the chance that we made an error, that we made a mistake because we don't know the whole population, okay? So something about this p-value is even though it's 0.0524, okay, if we want to compare this directly to alpha, we can round to 2 decimal places. Rounding to 2 decimal places, we have a situation where the p-value does equal alpha exactly, okay? So I'm gonna state the decision based on a couple alpha levels, okay? Because based on alpha of 0.05, which we chose when we were looking at our errors, the final answer is that, well, this is a little too close to call. And this kind of goes all the way back to where statistics is, there's a little bit of uncertainty in what we're doing here, okay? So at the 1% significance level, we would fail to reject HO, okay? Because if we chose alpha as 1%, then that means our p-value is large, fail to reject HO, okay? When alpha is at the 5% significance level, okay, it's just a little too close to tell, okay? Since we chose alpha as 0.05, that is going to be the decision that we have, okay? And so the conclusion is just, yeah, it's too close to call. We don't really have enough evidence one way or the other, okay? So in all actuality, if this were a situation that were to happen, if you're doing statistics for some company in the future, what you would have to do is like, well, you have to go out and you have to collect a new sample. Have to go out, collect a new sample, start the test over from the beginning, okay? If we chose alpha as 10%, then, or the 10% significance level, then the p-value would be low enough and we would reject HO and accept HA. So a little bit different. This case study gives us an opportunity to talk about, well, what happens when alpha does, or when your p-value does equal alpha, okay? It's pretty rare. It doesn't happen all the time. But again, if this were to happen, you would just have to go out, collect a new sample to make a better conclusion. All right, so now since we chose alpha is 0.05, I want to start with building a 95% confidence interval here, okay? So we had a large sample, so our formula is x bar plus or minus our z value times s over square root of n. Now, since 95% confidence interval is what goes along with alpha of 0.05, we should get a confidence interval that supports this decision of it's a little too close to tell. All right, so go ahead, pause here, practice calculating this confidence interval, and go ahead and also practice writing the interpretation of the confidence interval, since now we have a problem with context. Okay, 1.96 is the value from the t-table, 2.733 comes from the problem, 0.762 comes from our problem, 90 comes from our problem. When you calculate those, you should get 2.58 to 2.89. Okay, so how to interpret this confidence interval? So again, notice I don't have the symbol mu in here. I say what mu is in words. Okay, we are 95% confident that the average GPA of students at the university that enroll in an introductory statistics course is between 2.58 and 2.89. So over here, I'm going to write our HA mu does not equal 2.889. Let me double check that that is the right number we were working with. 2.889. Okay, so we have that mu is somewhere between 2.58 and 2.89. 2.89, that is just barely on the edge of 2.889. Again, if we mirror this and we round to 2 decimal places, it's 2.89, okay? It is just right there on the edge, which helps support our decision where it's too close to tell, okay? It's just a little too close to make a very definitive choice one way or another with this data set. Okay, just to get some practice with confidence intervals, let's build a 99% confidence interval, all right? And so again, this 99, I'm gonna switch colors for a moment. This 99% confidence interval should support this decision we made at the 1% significance level. So plugging in all our numbers again, now with 99% confidence interval, the Z table value is 2.575. Plug all those in, you should get 2.53 to 2.94. Again, take a moment, practice interpreting this confidence interval. We are 99% confident that the average GPA of students at the university that enroll in an introductory statistics course is between 2.53 and 2.94. At the 1% significance level, we fail to reject HO. We do not have evidence that the mean is different from 2.889. And look, 2.889 is within this confidence interval. So if mu is within the confidence interval, then it's not different from 2.889, which again is what we concluded at the 1% significance level. Okay, that's going to be all for this week's notes. That is really all the information you need to be preparing for exam 3. So something that we're going to start going over next week is when you get a problem, being able to decide between case study 2A and case study 2B. All right, you guys have a great day.